Hello class, this is Module 2. Let's get started. In Module 2, we'll talk a lot about structures needed for statistical inference. The first thing we need to understand is estimating population proportion. So proportion can be calculated by dividing the number of elements that fit a criteria by the sample size. We usually write a sample proportion as P with a hat on top of it. So in case you can't see the small fonts, we write P hat for sample proportion, and that's equal to the number of elements of interest divided by the total number of elements available. For example, in a sample of 50 adults, 20 wear glasses, so the proportion is 20 divided by 50, which is 0.4. In a parking lot with 200 cars, 15 are red, so the proportion of red cars is 15 divided by 200. A sample proportion is used to estimate the value of a population proportion of quantitative data. So sample proportions is a point estimate. So that's a key term here. A sample proportion is a point estimate. A point estimate is a single value from a sample used to approximate a population parameter. So again, this is a very important idea. I'll emphasize again. A point estimate is a single value from a sample used to estimate a population parameter. So what are population parameters? Those would include mean, variance, standard deviation, median, mode, and so forth. For example, the Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. The best possible estimate of proportion, the population proportion, is the sample proportion. So P hat is equal to 0.85. So even though Pew Research Center sampled 1,007 adults, we can infer that the 0.85 computed for the particular sample also applies to the population of all adults in the United States. So the question is, where did the 1,007 come from? We'll examine that in a few minutes. Sample proportion is used to construct a confidence interval to estimate the value of a population proportion. Okay, so let's think about what these words mean. Okay, the sample proportion is used to construct a confidence interval. Okay, so an interval is like a line segment on a number line. So suppose you have your number line, your x-axis. Okay, and so the sample proportion is used to construct an interval. And so in some of the topics in this module, you'll be required to calculate the left endpoint of the interval and the right endpoint of an interval. So we need to find the sample size to estimate a population proportion. Let's do an example. 50 people are selected randomly from a certain population, and it is found that 12 people in the sample are over 6 feet tall. What is the point estimate of the proportion of people in the population who are over 6 feet tall? Okay, so to do this particular problem, okay, it's pretty straightforward. We would just take 12 people, the 12 people are over 6 feet tall, and we divide it by the number of people, which is 50. Okay, so let's see. I can pull up my calculator. And so 12 divided by what? 50, right? Is 0.24. So choice C, 24% of the population in the sample is over 6 feet tall. Let's look at another example. 459 randomly selected light bulbs were tested in a laboratory. 291 lasted more than 500 hours. Find a point estimate of the true proportion of all light bulbs that last more than 500 hours. Okay, so we can assume that the point estimate derived from this sample applies to the population. So we have 291 bulbs lasting more than 500 hours. So 291 out of a sample size of 459 randomly selected bulbs. And so that gives us a proportion of 0.634%. And note that I use my equation editor to write the formula for the sample proportion. 291 divided by 459 right here. So let's talk about estimating population proportion. A range or interval is used to estimate the value of a population interval. Okay? We have this term called confidence level. A confidence level is the probability that the confidence interval contains a value for a population parameter. Okay, so we also have what's called a significance level, which we call alpha. Alpha is the quantity used to determine the confidence level percentage. So alpha values are typically 0.01, 0.05, and 0.1. A confidence percentage is 1 minus alpha. So let's interpret what these definitions mean. A confidence interval of 0.828 less than proportion less than 0.872 with an alpha of 0.05 means that we are 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion. This means that if we were to select many different sample sizes of 1007 elements and construct the corresponding confidence intervals, 95% of those confidence levels, check that, confidence intervals, would actually contain the value of the population proportion. Okay, so basically what's going on here is you generate a large number of samples. Each sample has a size of 1007. From that sample, you can calculate a confidence interval. And each of those confidence intervals are determined to have a confidence level of 95%. So for each of those confidence intervals, you are 95% assured that the actual population proportion lies within that interval. So that means if you have 1,000 confidence intervals, you have 1,000 confidence intervals, 950 of those confidence intervals are guaranteed to contain, well, not guaranteed, 950 of those confidence intervals are likely to contain the actual population proportion. 50 of those are likely not to contain the actual population proportion. Let's talk about critical values. A standard z-score can be used to distinguish between sample statistics that are likely to occur and those that are unlikely to occur. Such a z-score is called a critical value. The sampling distribution of sample proportions can be usually approximated by a normal distribution. So what this bullet means is that if you have a large number of sample proportions, so let's go back to our original example. Suppose I have 1,000 samples, each sample of 1,007 elements. From each of those samples, I get a sample proportion. Okay, so if I take those 1,000 sampled proportions and I distribute them, then we have what's called the sampling distribution, and it's going to be bell-shaped. So the sample proportions from 1,000 samples are going to be stacked kind of like this bell-shaped curve. A z-score associated with the sample proportion has a probability of alpha over 2 of falling in the right tail and an alpha over 2 probability of falling in the left tail. The z-score separating the tail regions is commonly denoted by z alpha over 2 and is referred to as the critical value because it is the borderline separating z-scores for sample proportions that are likely to occur from those that are unlikely to occur. Okay. All this means is that for a particular alpha, okay, and alpha are typically 0.01, 0.05, and 0.1, we use it as an index for a particular z-score, a standardized z-score. And we want to find the probability of some event occurring based on a standardized distribution. So for given confidence levels, alphas, alpha over 2, 1 minus alpha over 2, we have these critical values. So let's take a look at the standardized table to show you where these numbers come from. I posted earlier a number of statistic tables that you can use. You can print these out and use these rather than having to flip through your ebook. So one of the tables I sent you was the standard normal table, and here it is. So for a confidence level of 90%, that translates to an alpha of 0.1. So the way we get this alpha of 0.1 is we take the confidence level and we convert it to a fraction, which is 0.9. Then we subtract that fraction from 1, so 1 minus 0.9 is 0.1. That's alpha. Now alpha over 2, of course, is 0.1 divided by 2, which is 0.05. So 1 minus alpha over 2 is 0.95. So to find a critical value of z alpha over 2, okay, what we do is we look up 0.05 in our standard normal table. So going here, looking at our table, we want a z-score that corresponds to 1 minus alpha over 2. That's the interpretation. So we get alpha over 2, subtract it from 1, we get 95%. So we want to know which z-score corresponds to 95% of the area under the curve. So we go into our table, our standard normal table, and we look up where the location of 0.95 is. And so that's between these two numbers right here. So you intersect this row, okay, right there. So 1.6. Now 0.95 is between these two values, so you can kind of interpolate. So it would be 1.6, okay, and then you would add 0.045 to 1.6, and that's where this number comes from. So why is it plus or minus? Well, depending on, well, because the table is multivalued, okay. So 0.95 occurs here on the positive side, okay, for positive z-scores, okay. And then if we look at the negative z-scores, okay, we have to find 0.05. So 0.05 occurs between these two numbers right here, okay. And so that corresponds to negative 1.645 right here. So that because of table symmetry. Okay, so this negative 1.645 corresponds to alpha over 2. Okay, alpha over 2, which is 0.05. 1.645 corresponds to 1 minus alpha over 2. So if alpha over 2, what we do is we take alpha over 2 and we get right here. We find the z-score negative z alpha over 2 right here. And that corresponds to negative 1.645. Okay. All right, so let's see what else we can do. So we have this margin of error. When data from a simple random sample are used to estimate a population proportion, the margin of error, denoted by uppercase E, is the maximum likely difference with probability 1 minus A, such as 0.95, between the observed proportion and the true value of the population proportion P. So for example, if the confidence level is 93%, then alpha is equal to 0.07. Okay, so the way we got alpha equals 0.07, convert 93% to a decimal and subtract it from 1. Alpha over 2 is 0.035. All right, so then we subtract 0.035 from 1 and we get a value of 0.965. Why do we subtract from 1? Because we want the area probability in the right tail, but the z table gives us the area from the left. So looking at 0.965 in the z table, we see that it's closest to 1.81. All right, so okay, and so this would be the z value for 0.945. So let's look at the standard table. Okay, so we want what? 0.965. 0.965. 0.965. Okay, so 0.965 is right about here. If it's roughly 0.9649 is the nearest number. It's closer to 0.9649 than it is to 0.9656. So without having to interpolate, we intersect this row with the column, which is 0.01. So we add 1.8 plus 0.01 to get 1.81. So that is the z alpha over 2 for excuse me, for alpha equals to 0.07 and a confidence level of 93%. Okay, so let's do an example. Find the value of z alpha over 2 that corresponds to a confidence level of 91%. Okay, so the way we do that is we compute our alpha. So confidence level is equal to 91%. Okay, so alpha is equal to 1 minus 0.91, which is equal to 0.09. Okay, so what is alpha over 2? So alpha over 2 is 0.045. Okay, and so we subtract that from 1, and so that would be 0.955. All right. So now, to get the z value, the z-score for this, we have to find 0.955 in our table, our standard normal table. So where is 0.955? 0.955 is closer to, so it's kind of between what? 1.6 and 1.7? Oh, let's see. Actually, it's closer to, okay, 0.955 is pretty close to, let's see, it's 0.005 from here, and, okay, so it's pretty close to this. So we can pretty much say that the z-score is going to be, well, let's see, 0.955. To get to 0.955 here, we would have to add what? 0.0005 here, and to get to 0.955, so this number right here, 0.9554, is closer to 0.955 than 0.9545. So we can deduce then that z alpha over 2 is equal to 1.7. Is that a choice? Yes, so you would select choice A. Okay, next question. Find the critical value for z alpha over 2 that corresponds to a degree of confidence of 98%. Okay, so we have a confidence level of 98%. Okay, alpha equals to 0.02 because, all right, then alpha over 2 is equal to 0.01. So we subtract that from 1 and we have 0.99. Then we go to our standard normal table and we look for 0.99. So where is that? So that would happen right about here. So that looks to be about 2.30, 1, 2, 3. So about 2.33 from the standard normal table. And so here's the illustration. Okay, so let's talk about the standard deviation of a sample proportion. The standard deviation of a sample proportion is equal to this formula, the square root of p hat times q hat divided by n. So p hat is the proportion, the sample proportion. Q hat, of course, is 1 minus p hat, and n is the sample size. So this would be the standard deviation of a sample proportion. Why do we need to know this? Well, we can find the margin of error for proportions or maximum error of the estimate. Okay, so this uppercase E is called the margin of error for proportions. Another name for it is the maximum error of the estimate. Okay, and that's equal to Z alpha over 2 times the standard deviation. So let's do an example. Assume that a sample is used to estimate a population proportion P. Okay, so we're going to use a sample to estimate a population of proportion P. Find the margin of error, E, that corresponds to the given statistics and confidence level. Okay, round the margin of error to 4 decimal places. All right, so we have a 98% confidence, so confidence level is 98%. Okay, and the sample size, okay, is what, 800? And the sample proportion, okay, the success is 40%. So P is equal to 40%. P hat is equal to 40%. Of course, Q hat is 1 minus P hat, which is 0.6. Okay, so now the formula is, for the margin of error, is Z alpha over 2 times S. Okay, remember, S is the standard deviation of the sample. Okay, and since the standard deviation of the sample proportion is this. Okay, so the only thing that we need to look up is Z alpha over 2. Okay, so alpha is 0.02. Alpha over 2 is equal to 0.01. Okay, so 1 minus alpha over 2 is equal to 0.99. Now, from the previous problem, we know that the z-score that corresponds to this, okay, was 2.33. So from the previous problem, okay, so now all we have to do then, the margin of error is equal to 2.33 times the square root of okay, that's the Q value. Okay, this is the success, this is the failure. Sorry, I flipped them, but it's okay. And then we have, what, 800 is our sample size. Okay, so let's run this in the calculator, run the numbers here. So I want, for my margin of error, 2.33 times the square root. Okay, that would be 0.6 times 0.4 divided by 800. Okay, so we take the square root of all of that, and we get to 0.04. So our margin of error is 0.0404. Okay, is that a choice? Yes, so it would be choice C. Okay, all right. So the confidence interval for estimating a population proportion. So remember what the confidence interval tells us. Okay, the confidence interval tells us a range where the population proportion is likely to fall based on sample proportions. Okay, so here's the nomenclature. P is the population proportion, P hat is the sample proportion, N is the number of sample values, E is the margin of error, and Z alpha over 2 is the z-score separating an area of alpha over 2 in the right tail of the standard normal distribution. Okay, so the confidence interval will be P hat minus the margin of error as the left endpoint, P hat plus the margin of error as the right endpoint. And these are the ways you can formulate it. 3 different styles. So if you have to do this computation in any report format, you can choose either one, but make sure you use the equation editor. All right, so let's do an example. In the problem described earlier, we noted that a Pew Research Center poll of 1,007 randomly selected adults showed that 85% of the respondents know what Twitter is. The sample results are n equals 1,007 and population proportion is 0.85. Okay, the sample, check that, not population proportion, but sample proportion. P hat is sample proportion. Okay, population proportion is P. Sorry, I didn't see the hat. So the question is, find the margin of error, E, that corresponds to a 95% confidence level. Okay, so let's do A. All right, so we have N equals to 1007. Sample proportion is equal to 0.85. Okay, and confidence level is 95%. Okay, did I not give a table earlier? Let me see. I did not. Oh, okay. So for confidence level of 95%, okay, we know that the critical value is 1.96. So we can use this table rather than having to flip back and forth to the standard normal table. This is kind of a condensed table. Again, we know that alpha is equal to 0.05, alpha over 2 is 0.025, 1 minus alpha over 2 is 0.975. And so the critical value, which I'll call CV, is equal to 1.96. Okay, so let's go back to the problem again. Find the margin of error. Okay, so the margin of error, okay, well, we have the previous formula. So this is Z alpha over 2. Okay, so the margin of error is equal to Z alpha over 2 times the square root of this quantity, okay, which is equal to 1.96 times the square root of, okay, so P hat is 0.85, Q hat is 0.15, and then our sample size was 1007. Okay, so I'll let you punch that on the calculator, but that's the setup, and it should agree with hopefully. Okay, well, okay, I guess I'll go ahead and do it. Because the other problems depend on the answer, right? Okay, so we have margin of error is 1.96 times square root of 0.85 times 0.15 divided by sample size, 1007, close. So our margin of error is 2.2%, right? Okay, so 0.02205. Okay. All right, so that's our margin of error. That's the answer to part A. Part B asks, find the 95% confidence interval estimate of the population proportion. Okay, so we know that the formula is this. So we want the interval will be this. Okay, and so what is P hat? P hat is 0.85. So we have 0.85, and E is 0.0221. Okay. Okay, so that would be the interval which we're likely to find the population proportion 95% of the time. Okay, so we're basically 95% confident that we can find the true population proportion in this interval. So let's run the numbers. So we have 0.85 minus 0.0221. Okay, so the left endpoint is 0.8279, less than the population proportion. Okay, and then we have 0.85 plus 0.0221. So it's 0.8721. 0.8721. All right, so we have that. Boink. Okay. Okay, so that's the answer to part B. Based on the results, can we safely conclude that more than 75% of the adults know what Twitter is? Well, we can, because 75%, or 0.75, is to the left of the left endpoint. Okay. Now, if 75% occurred to the right of the left endpoint, then we could not necessarily conclude that more than 75% of the adults know what Twitter is. Assuming that you're a newspaper reporter, write a brief statement that accurately describes the results, that includes all of the relevant information. Okay, so let's look at this. All right, so here's our our margin of error. Our z value was 1.96. We found that from the table. The 95% confidence, okay. And all right, so the summary, and this is what you'll have to include in your reports, is that 85% of US adults know what Twitter is. Where does the 85% come from? Well, that was in the information given. That was your sample proportion. That percentage is based on the poll. Okay. So here's the key sentence right here. In theory, 95% of such polls, the percentage should differ by no more than 2.2% percentage points in either direction from the percentage that would be found by interviewing all adults in the United States. So what this means is that if you took a large number of polls, okay, 95% of those polls would be within the sample proportion of 95% of those polls would be within 2.2% of the actual population proportion. Okay, so this is the key sentence that you'll have to include in your assessment of any kind of confidence interval computations. So let's do another example. Use the given degree of confidence in sample data to construct a confidence interval for the population proportion P. All right, so in this case, we have n equals to 195. So that's our sample size. Okay, and then x, so the number of successes in that sample is 162. Okay, and we want a confidence level of 95%. Okay, so what is our p hat? So p hat is equal to 162 divided by 195. Q hat is equal to 1 minus p hat. Now, a confidence level of 95%, okay, translates to a critical value of z alpha over 2. So we can go back to our table. Okay, 95% corresponds to alpha equals to 0.05. So let's go back. 95% alpha over 2. So we want this value, 0.975. And that corresponds to a 1.96 critical value. So we want 1.96. Okay. So back to the problem. Okay, so we need our margin of error now. So our margin of error is equal to z alpha over 2 times the square root of p hat q hat over n. Okay, so that's 1.96 times the square root of, okay, so our sample size is 195. Oops, 195, right? Okay, times, okay, so n is 195, p hat is 162 over 195, and our q hat is 1 minus 162 over 195. Okay, so that's a little bit complicated, but nevertheless, we didn't have to do too much. I think the only math challenge here is to see if we can punch this in on our calculator. Perhaps we can use Excel for this. Let's see. I haven't tried this, so bear with me. So here's Excel. So what do? You type equals 1.96 times square root. Okay. Okay, so we want 1 divided by 195 times, okay, 162 over 195 times 1 minus 162 over 195. Okay, and so yeah, so the parentheses balance, and so let's see if I type this in right. Okay, so E is 0.0526. Okay, I'll use 263. Okay, so I'll use 4 digits, 4 significant digits. Okay, so that's our margin of error. So what do we need to do? I lost track of the question. So we want a confidence interval. Okay, so our confidence interval then would be p hat minus 0.05263 less than population proportion less than p hat plus 0.05263. Okay, so what is p hat? So p hat is 162 over 195. Okay, so maybe I should go back to Excel. Okay, so we want 162. So the left endpoint of our confidence interval will equal to 162 over 195 minus, okay, and then we can use that. So that's 0.7781. Okay, so we have 0.7781 less than p. Okay, and then we have the right endpoint would be 162 divided by 195 plus oops, I need an equal sign, don't I? Equals 162 divided by 195. Why do I keep typing minus? Equals, okay. 162 divided by 195 plus that. Okay, so the right endpoint would be 0.8834. Okay, is that a choice? Let's see. 778. Yeah, so it looks like choice C would be the most logical choice here. Okay, all right. So we have confidence intervals and confidence levels. All right, so let's move on to the next topic. Sample size. Okay, the sample size is the minimum number of items that must be obtained in order to estimate a population proportion. Okay, so to compute the sample size, you extract n from the margin of error formula, and here's the formula. Okay, so when p hat is known, we can use this formula because we know q hat. When we don't know p hat, then we can replace the product p hat times q hat by the factor 0.25. So let's do an example. Use the given data to find the minimum sample size required to estimate the population proportion. So the margin of error is 0.028 and the confidence level is 99%. Okay, and unknown. Okay, so in this particular question, the unknown sample proportion. So the sample proportion is unknown. So we have to resort to this second formulation. Okay, so the way we would solve for the sample size. Now, the sample size is the minimum number of the minimum size of a sample so that you can get a valid statistical inference. Okay, so n is equal to z alpha over 2 squared times 0.25 divided by e squared. And so the margin of error in this problem was 0.028. So I'll go ahead and wire it in. Okay, so where 99% is our CL, right? Okay, so what Z alpha over 2 corresponds to 99%? Well, we can go back to that table, right, at the start of this document. So let me go back. Here, 99% corresponds to a Z alpha over 2 of 2.575. Okay, so we will have N is equal to 2.575 squared times 0.25 divided by 0.028 squared. So if your sample size is anything less than this number we're about to calculate, then your statistic is wrong. Okay. All right, so let's see here. Let me pull up my Excel. So I want equals 2.575 squared times 0.25 divided by 0.028 squared. Now, one thing for you guys who struggle with math a bit, this caret symbol, this means exponentiation, and note that exponentiation has higher precedence than multiplication. So this is not to be interpreted as 2 times 0.25, but rather 2.575 squared, then you multiply it by 0.25, then you divide it by, okay, again, the exponentiation takes precedence, so you square that before you do the division. Okay, and so the sample size is 2,114, I would believe, and I'll check that. Okay, and you round it. So is that a choice? Yeah, so 2,115. So in this case, they took the fractional part and rounded up, which is probably a good practice. So I would choose choice A. Okay. All right, what next? Okay. So methods for using the sample mean to make an inference about the value of the corresponding population mean when we don't know the population standard deviation. All right. So in many statistical computations, you very rarely know the population standard deviation. So how do you make inferences about the population mean when you don't know the population standard deviation? Okay, and so in this case, we use a sample mean, okay, and we use the t-distribution table. And the t-distribution table is one that I posted in the announcements section. You can use that, or you can use the one in the back of your book. So the sample mean, okay, sample mean is always x bar, and it's the best point estimate of the population mean. Okay. All right. So to reiterate, the sample mean x bar is typically the best point estimate for the population mean. We can use sample data to construct a confidence interval for estimating the value of a population mean, and we should know how to interpret such confidence intervals. All right, so we don't know the population standard deviation, but we can still calculate a confidence interval for estimating the population mean. All right, so the margin of error is this new statistic called T alpha over 2. Okay, so the margin of error is this, and I'll show you how to calculate that. So T alpha over 2 times the sample standard deviation. So you know your sample data, so you should be able to get the sample standard deviation divided by the square root of the sample size. Okay, so T alpha over 2. So when you go to calculate T alpha over 2, you know N, and you have to get this parameter called degrees of freedom, which is N minus 1. I won't go too much into the definition of degrees of freedom, but all we know is that it's a parameter that you need to look up a T value, a critical value it's called. So, for example, find, what does the question say? Find the appropriate critical value for the following: 99% confidence level n equals 17 and population standard deviation is unknown. Population appears to be normally distributed. Okay, so you need this notion, the fact that the population is normally distributed is the indicator. Okay, so you use this clause, population appears to be normally distributed, as well as the standard population standard deviation unknown. These two items, you use that as indicators that you'll have to use a t-distribution table. Okay, so let's see what we've got here. Okay, so have to use the t-distribution table, or it's often called the student's t-distribution table. So I'm going to use the one I posted in the announcements section. Now we have n equals 17, so the degrees of freedom is 16. 99% confidence level, so we know with 99% confidence level, what is our alpha over 2? So go back here. For 99%, alpha over 2 is 0.005. Okay, so 0.005. I'll try and remember that. What else? Okay, so it has to. So looking at the choices, we can't use the standard z-score. So you can reject A and C off the bat. So it's the answer is going to be either B or D. So 99% confidence level. So let's look that up in the student's t-table. We have alpha. So let me expand it to 100%. So we have degrees of freedom of 16, right? So you go to this DF column, the first column in our table, 16, and T of 0.005, which is this column right here. So we intersect this column with this row to get 2.921. So the answer is choice D, 2.921. Okay. Another example. Find the critical value for T alpha over 2 corresponding to n equals 12 and 95% confidence level. Okay, so the degrees of freedom are 11, right? And we know with alpha equal to 0.5, okay, so alpha is equal to 0.5. We need T alpha over 2. So T alpha over 2 corresponds to what? Alpha over 2 is 0.05 divided by 2, which is 0.0025. And we have a degrees of freedom of 11. Okay? So, let's see. Let me pull up my t-distribution table. So we want 11, this row, intersect it with what? 0.25, right? Which is here. So it's 2.201. All right, so let's look at the two different methods for solving this. Notice in the first approach, alpha equals to 0.5, okay? So that's the two-tailed. That's the area in two-tails. And so you could go here. Let's see. I'm trying to see here what the distinction is. Okay, they still sliced alpha in half, though, before proceeding. Okay. And let's see, does this table do two-tailed? Okay, so values for alpha. Okay, so this is, okay, two-tailed. Okay, for two-tailed test. All right. Yeah. Okay. So, okay. Which is what we're doing. We're doing a two-tailed test. Okay. And the area. Okay, the critical value. Yeah, the area in each tail. Okay. All right. So in the distribution of a population, okay, no, check that. If the distribution of a population is normal, then this distribution is a student t distribution. Okay, and so the t statistic can be found in terms of the population mean and the sample standard deviation and the sample size. All right. Okay, so all right. So we've done this. The confidence interval for the estimate of the population mean when we don't know the population standard deviation. Okay, the margin of error is thus right here. All right, so let's do this particular problem. Use the confidence level and sample data to find the margin of error E. So college students' annual earnings, 99% confidence, sample size of 74, sample mean is this, and the sample standard deviation. Okay, so we want to find the confidence interval that contains the population's annual earnings based on the sample properties. Okay. All right, so we do not know we do know sample standard deviation. Okay, but what are we missing here? We don't have, okay, the margin of error. So we have S. Oh, okay, so the reason why we would have to use the t statistic for this problem is that we don't have any information that indicates that this population is normally distributed. Okay, so when that's not the case, then we can resort to a t statistic. Now, if it said the population were normally distributed, then you could use z alpha over 2. Okay. All right, so let's proceed. Blank page. Okay, so what we're chasing here is the confidence level. Okay, so the x bar, so we want this formula right here. So we need this computation where the population salary, mean salary, resides. So it's going to reside 95% of the time. Or check that, we're 95% confident that the population average salary will be in this interval. All right, so we have x bar is already given to us, so that's 39.67. Okay, so now if this were like a end of live lesson quiz, and if you wrote this, then you could get partial credit. Okay, all right. Okay, so what else? We need to find E, right? Okay, so E is equal to T alpha over 2 times S over the square root of N. Okay, so we have S, right? Standard deviation is 874. And N is 74. Okay, so we've got that. So the only thing we're missing is T alpha over 2. Okay, so we have degrees of freedom is 73. And alpha is what? 0.01. So alpha over 2 is, for a two-tailed test, this. Okay, so we need the t statistic for that. Can we find it from this t table? I don't know. Okay, so we would probably need to use Excel to find the t statistic. Okay. Okay, so let's see. How do we can we use Excel to find the t statistic? Let's see. Is it t-dist? T-distribution. Use Excel to find t statistic. Statistic. So click data. So do I have data analysis on this machine? Data. Okay. I don't know if I have data analysis, data tools. Okay, so if you don't see data analysis, load the data. Okay, so I need to load the data analysis. Data, let's see, data tools. Okay, so we need to load the data analysis tool pack, Excel. Okay, so, alright, so what does it say? Click the File tab. Slide it open. Okay, so to load data analysis tool pack, you go click the File tab, Options, and then click the, what, add-ins? Add-ins. Okay, and then we go to the, oops, sorry. Okay, and then we go to Manage, and then click Go, and then we want the analysis tool back. Okay, so this is something you'll have to do for your Excel if you want to use some of the statistical packages. So we have that. Alright, so now we can go back and see if we can use Excel to calculate the t-statistic. Okay, so step 4, click the t-test 2 sample unequal variance. Okay, so alright, so let's see here. So then we go to data. Okay, so data analysis. And then it says t-test 2 sample assuming unequal variances. Okay, so t-test assuming unequal variances. Okay. Alright, so can we do this? So we actually want an interface that gives us degrees of freedom and an alpha over 2. So I don't think we want this particular one. Let's see. Paired samples. Let's see what this does. Wants a variable range. We don't have data. Can Excel be used to find a t-statistic? Let's check this again. Okay. Okay, probability and degrees. Okay, so we want to use T and V. Probably T and V. Okay, so it's T and V. Okay. T. Alright, so let's try that. Let's cancel out of this. So let's go equals T and V. Okay, what was that? How did we do that? Okay. So we go, oh, okay, we need to give it data. Okay, so in this particular problem, our probability is what, 95%? Our alpha was, what was our alpha? Alpha was 0.01. Okay, 0.01, and the degrees of freedom are 73. Okay, so we need 0.01 and 73 for T and V. Okay, so equals T and V. Probability is 0.01 and degrees of freedom are 73. Okay, so that would be our t-statistic. So let's make sure, let me make sure that I'm right here. Let's see. Yeah, so I think we're good to go with this. Okay, so Excel gives us a 2.6449. Okay, so let me check. Okay, so let's see. Okay, so 2.6. Okay, all right, so we can go with that. And so now we need our, now we can calculate our margin of error. Sorry about the little detour. Oh, I didn't anticipate this. So E is equal to 2.6449 times S, which is 874, divided by the square root of 74. So what is our margin of error? Okay, so I'll need my calculator. So I have 2.6449 times 874 divided by the square root of 74. Okay, and that is 268.72. Okay, so that's our margin of error for the sample. Okay. All right, and so now we have to subtract that from 3967. Okay, so we go 3967 minus 268.72. And so that's 3698. So that is 3698 less than the mean salary, less than, okay, and then we need to go 3967 plus 268.72. Okay, and that's 42.35. Okay, now let's see. So let's check. Let's compare this against what's in our t-distribution table. So the t-distribution table obviously doesn't process the degrees of freedom we have. So let's check the authenticity of this Excel t-inverse function. Okay, so let's go back to our student t-table. And so let's try 80 as our degrees of freedom with what? An alpha of 0.01. Okay, so that corresponds to an alpha over 2 of 0.005. So that would be, okay, so that would be the second to last column, 80. So 2.639 if we were to use this table. Okay, so let's see here. What would t inverse of Excel be for an alpha of 0.01? T inverse of, okay, so the probability is 0.01, right? And the degrees of freedom would be, let's try 80. 2.639. Okay, yeah, so I think you can do it. This would be a good estimate for your critical value, your T alpha over 2. You can do it that way as well. I believe my way is more concise. Okay, so that's how you can use Excel to calculate T values, critical values for T. Okay, so where are we at now? Pull up my Word document. Okay, so we've done this one. Okay, so in this particular case, they used DF of 80 in alpha, so they chose not to use Excel to solve this particular problem. We did, and I think our answer is probably a little bit better. So the conclusion is, using this estimate, we are 99% confident that the average annual earnings of college students is between, well, this particular worked example versus my particular worked example. And I believe my particular worked example would be more acceptable. The fact that I used a more precise computation for the T statistic. Okay, so we're 99% confident that the mean salary is here. Okay, all right. So let's go on to the next topic. Confidence interval for estimating a population mean with standard deviation unknown. So we just, with population standard deviation unknown. Okay, so how does this compare? In the previous problem, population mean with sigma unknown. In this problem, okay, so it's the same. So in this particular case, they're using the Z statistic with, okay, so, I beg your pardon. This is, okay, so in this particular problem, we just worked through population standard deviation not known, okay. Now with the population standard deviation known, what? Sigma known, okay, then we can use the Z statistic as well as sigma. Okay, so this would be the standard deviation of the sample right here times the Z statistic. Okay, and I believe we've done that. We did that in module 1. Okay, so next topic, or another example. So 30 randomly selected students took the calculus final. If the sample mean was 95 and the standard deviation was 6.6, construct a 99% confidence interval. Okay, so we have the standard deviation of the sample. We have the sample mean. Okay, so since we know sigma and we have the sample size, so then we can just use the margin of error. And we want a 99% confidence interval. Okay, so in this case, for the mean score, right? Okay, so the mean score would be, okay, if the sample mean was 95%. Okay, so the way you would solve this problem is you would have sample mean, which is what? X bar, right? Minus your margin of error less than the population mean, which is less than sample mean plus the margin of error. So this is what you're chasing right here. You want this kind of report analysis. Where does the population mean reside? And that you're 99% confidence, right? 99%. Okay, so 99%. Now since we have sigma, so we can use the Z alpha over 2 stat. Okay, and so that means that we can go back to our table, which I have right here. Okay, I repeated the table again. So with 99%, a Z alpha over 2 lookup would be 2.575. Okay, so 2.575. Okay. All right, so sample mean was 95, so, well, we need E, right? So E is equal to Z alpha over 2 times sigma over the square root of n. So that would equal to 2.575 times sigma, which was what, 6.6? Population standard deviation. And the sample size was 30, right? Okay, so we need to calculate that margin of error. So we have 2.575 times 6.6 divided by the square root of 30. Okay, and so that is 3.1 is our margin of error. Okay, so that means that the mean score, we're 99% confident that the mean score will occur between these two numbers. Okay, plus 3.1. So what is 95 minus 3.1? 91.9. So to 98.3. So probably the better choice would be choice B. Or choice, well, let's see, oh my gosh, those numbers are pretty close, aren't they? There's not much difference between choices B or C. We can probably rule out choices A and D. Okay, probably choice C. I would go with choice C. Let me check my notes. See if I did it right. 2.75. Perhaps was my Z alpha over 2 off? 2.575. Okay. Let me check. Let's see. It's a tough call. I think in many cases the book will require that you use 4 digits. So to clarify, I probably should not have rounded to 3.1. Okay, so I think that's the point of this question, as to be careful how you round. Your 6.6 divided by so 91.897. I get there, and it's odd. How am I getting a different number now? So it's 91.897. Yeah. I would say choice C would be the better one. They were probably using Excel for this. Let's see. Does Excel have a Z inverse? Let's try it. Let's experiment around here. Z inverse. No, I don't know what the no, I'm not sure what the Excel formula would be. We'll find that out later, I'm sure. Okay, Well, I think choice C would probably be the better one for this particular problem. Let's go on to another class of problems, the final class of problems. So we want to estimate a population standard deviation. To do so, we'll need the chi-squared distribution, which is an asymmetric distribution. The chi-squared distribution changes shape based on the degrees of freedom. All right, so I'll show you how you leverage this. Okay. First of all, let's see how we would read the chi-squared distribution. Okay, so for this, what I did post in the announcements was a chi-squared distribution table. So you can use that, or you can use the one in the back of the book. So let's consider this example. This example treats how to read from a chi-squared distribution table. So find the critical value chi-squared right, R stands for right, corresponding to a sample size of 19 and a confidence level of 99% if the test is two-tailed. Okay, so to do this, the degrees of freedom, of course, will be 18. And the confidence level is 99%. So we want XR, right? X right, yeah. So the thing about a chi-squared distribution is it's kind of like an inverted Z distribution, in that when you read these values from the table, it gives you the area to the right, of the chi-squared statistic, which is written along the x-axis. So to do this particular problem, to read a chi-squared table, okay, again, our alpha is 0.01, okay, and it's a two-tailed test. So whenever you have a two-tailed test, you have to basically have alpha. So alpha is 0.01, have it, that's 0.05, 005, check that, and our degrees of freedom are 18. So we want the last column junctioned with 18. So the chi-squared R statistic would be 37.15. What is that? 37.1564. Okay, so that would be the choice for that. So you would answer choice D. Okay, now, so because the chi-squared statistic is the area to the right. Now, the next thing is find the critical value chi-squared L corresponding to a sample size of 19 and a confidence level of 99%. Okay, so in this case, the alpha over 2 value is again 0.005, but okay, to get the left statistic, you have to subtract that from 1 to get 0.995 to get the chi-squared L statistic, because the this will give you the chi-squared L, because you want the area to the left, of the statistic. So we take 0.995, and our degrees of freedom are 18, so it would be 6.26477. Okay, so that would be choice A for this one. So chi-squared L means the area to the left of the statistic. So let me write this down. Okay, so to find chi-squared L at alpha, okay, what you do is you find okay, so you want degrees of freedom. Oh, let me not do that. Where's my eraser tool? Okay, so back to pen tool. So you want to find n minus 1, which is your degrees of freedom, and then you want to find 1 minus alpha over 2. Okay, so this is your, and this is for a two-tailed. To find, okay, two-tailed. So this might make things easier. So remember this for chi squared L. Okay, to find chi squared R, okay, you'll want to find n minus 1 alpha over 2. Okay, and that would be the area to the right. Okay, so the chi squared right area to the right. Okay, so you remember these two formulas, and I'll show you how they apply in applications. Remember, we use the chi squared distribution to estimate a population standard deviation. Okay, so we've answered those. Okay, so let's do an example. Find the critical value chi squared left corresponding to a sample size 19. Well, we just did that, right? We just did that. Okay, here's the solution. Alpha over 2 is here. 18 to the right of the critical value. Okay, so chi squared L corresponds to the left of the critical value. Okay, and so here's the explanation. Okay, so the confidence interval for the population standard deviation is this. Okay, if you know the sample size, the sample standard deviation, you can get the chi squared R and L values, and you can get an estimate for the population standard deviation. All right, so let's do an example. A simple random sample of 22 IQ scores is obtained whose standard deviation is 14.3. To construct a confidence interval for the population standard deviation sigma, we need to find the left and right critical values chi squared corresponding to a confidence level of 95%, sample and a sample size of 22. Okay, so the degrees of freedom is 21. So the alpha value is 0.05. Alpha over 2 is alpha over 2 is 0.025, right? Okay, so the degrees of freedom is 21. Degrees of freedom are 21, and to get the chi squared R value, okay, it would be 0.025, so it would be this 35.479, and then the chi squared L value would be 1 minus 0.025, 0.975, would be 10.283. And so, okay, so we want to subtract, no, we don't need to subtract. This, I'm looking at this magenta colored box here. The cumulative right area is 0.975 for this chi squared L value, and the cumulative right area for this is 34. Is 0.025. Yeah. So basically, what it's saying is the area to the right of this magenta colored value, this chi squared L value, is 0.975 of the area, and then the area to the right of this particular chi squared R value is 0.025. Okay, and so the interval, the confidence interval, would be, okay, so we wire up the numbers. 14.3 was given, right? 14.3 is the standard deviation, so we plug in chi squared R here, chi squared L here, and get these quantities. Okay, and so this would be for the variance. So the variance is here, and then of course you take the square roots of all terms in the inequality chain to get the interval for the population standard deviation. So you're 95% confident that the limits 11 and 20.4 contain a true value of the population standard deviation. Okay, so let's look at this particular example. Okay, so to find the standard deviation of the diameter of wooden dowels, a manufacturer measures 19 randomly selected dowels and finds that the standard deviation of the sample to be 0.16. Okay, Find the 95% confidence interval for the population standard deviation. Okay, so let's solve this problem. So let me pull up my white smartboard. Insert. Blank page. Okay. So the confidence interval, okay, what was that? The formula for the confidence interval of a population standard deviation is this very intimidating looking formula. So we need to make these calculations. Okay, so all of this is under the square root. Okay, so that's the left endpoint and then the right endpoint. Okay, so what numbers do we have to play with here? So we have 19 is our sample size, right? I forgot S squared here, didn't I? Oops, did I copy that improperly? I think I may have. Oh, it's in -1. Oh, sorry. I messed up. Get my eraser tool out. Okay, now back to pen tool. That should be it. Sorry, I wrote the formula down incorrectly. So n is equal to 19. What is our sample standard deviation for this problem? It was stated to be 0.16. Okay, and then alpha is 0.05, right? Because we're dealing with 95% confidence. So alpha over 2 is 0.025. Okay, so now we need our chi-squared statistics, right? Okay, so let's go to our chi-squared table. All right, so we have chi-squared L. Okay, so remember chi-squared L will be based on will be based on our degrees of freedom, which are 18, and 1 minus alpha over 2, which is 0.975. Okay, and then our chi-squared R. Okay, that will be based on degrees of freedom of 18 and an alpha of 0.025. Okay, so what is this equal to? So I'm looking for 18 and 975. Let me expand this a little bit better. 18. So 975 is this column, the third column, right? And 18. So 8.23074. And our chi-squared R would be based on these values, 18 and 025. So where's column 025? That would be this column. So roughly 31.5264. Okay. All right. So now we're ready to construct the interval. So the interval would be this stuff here. So let's pull up our, I guess we can use Excel here. Okay, so the left endpoint of the interval will be square root of n, which is 19, times s squared, which is 0.16 squared, divided by xr, which is 31.5264. 31.5264. Oh, found a typo. Oh, probably try it again. Yeah, I needed another parenthetical mark. Let's see. Okay, so that's 0.12. Okay, so 0.1209, right? So we have 0.1209 less than population standard deviation, and then the right endpoint would equal to this, right? So we would have, so I'll put it in this cell, equals to square root of n, which is 19, times 0.16 sample standard deviation squared, divided by chi-squared L, which is 8.23074. Okay, so that's 0.236612. Okay, so that would be my best answer, barring any computational errors I may have made. So let's see, is that a choice? 0.12 to 0.24. So I would say choice A is probably the better choice here. Okay, so one more topic. This is a rather lengthy lecture today. The values listed below are the waiting times in minutes of customers at the Bank of Providence, where the customers enter any one of three different lines that have formed at the three-teller windows. Construct a 95% confidence interval for the population standard deviation sigma and write a statement that correctly interprets the results. Okay, so we have these wait times. Okay, so to compute the standard deviation for this set of numbers, you probably should use Excel. Okay, so let's put our numbers in. Okay, so I won't go through all of the details of this problem, but you can see the demonstration here. So while I calculate the standard deviation, read the text there. Okay, so we have 4.2, 5.4, 5.8, 5.8, 6.2, 6.2, 6.7, 6.7, 7.7, 8.5, 8.5, 9.3, and 10. Okay, so we want the standard deviation of this. So this is equal to standard diva of this range. Okay, so yeah, 1.92. Now we need the chi-squared r. Okay, so the chi-squared r will be based on sample size, which is 1, 2, 3, 4, 5, 6, 7, 8. How many elements do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so in degrees of freedom would be 8. And we're 95, and so x chi-squared r would be based on 8 and what? 0.025, right? So let's look at our chi-squared table to make sure that this 19.023 is right. So chi-squared table. So 8 and 0.025. 0.025 is where? Third to last column. So 8 and 0.025. right here. They use 19.023, which corresponds to a degree of freedom of 9. So is that correct? I don't think so. Yeah, the degrees of freedom are 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the sample size is 9. So this solution is not correct. Why is it not correct? Because sample size is 9 and the degrees of freedom should be n minus 1. Okay, so we should use 8. So the chi-squared R statistic should be not 19.023 but 17. That should be 17.5345. Let's check the chi-squared L statistic. Okay, so that should be 0.975 and 8. Okay, so it should be 2.179. So it looks like these computations are incorrect. Let's see. Yeah, so this solution is wrong. These chi-squared values were based on a degree of freedom of 9 when 8 should be used. So you'll have to go back in and put in the correct values for chi-squared R and chi-squared L. So the interpretation is we are 95% confident that the true value of the standard deviation is between, well, okay, so that's not right, but nevertheless. Okay, all right, and so now the last problem I have for the lecture is, okay, so I have kind of this summary table. If you want to be 95% confident that that the population standard, okay, no, let me back up a bit. This table right here gives you sample sizes required to meet these criteria. Okay, so suppose you want to be 95% confident that your population standard deviation lies within the confidence of 1%, 5%, 10, 30, 40, and 50. Okay, so this basically says these are the sample sizes required so that your sample standard deviation will be 1% confident within 1% of your population standard deviation. So if you select 19,205 elements, okay, and then you compute the sample standard deviation based on a sample size of 19,205, then you can be 95% confident that you're within 1% of your population standard deviation. And the same goes for variance. And what is this? Okay, so the table is set up for 95% and 99% for sample sizes. Okay, so for instance, let me show you how you use this table. You want to estimate population standard deviation of waiting times at a fast food restaurant's drive-up windows, and you want to be 95% confident that the sample standard deviation, okay, the sample standard deviation is within 20% of the population standard deviation. What minimum sample size is needed? Okay, so you want to be within 20, you want to be 95% confident and 20% within reality. So if you want to be 95% confident and 20% within reality, okay, for what? A population standard deviation, okay, you want to have a sample size of 48. And it's practical. Okay, so why is this practical? Well, okay, well, it seems practical. I mean, there's nothing that says it isn't wrong. I mean, the number is not negative, or it's not a fraction, or it's not huge like a million or so. So qualitatively, I would say that the figure is reasonable. Okay, all right, so that takes care of the lecture content for Module 2. I'm going to go ahead and close this out. Now, if you have any questions, as always, you can contact me, and I can guide you through any difficulties that you may be having. So let's see what the deliverables are so far. You have your Phase 2 report, which is due tonight at midnight, or Saturday at midnight. Now you have a homework assignment, which is due. Well, let's check. Let me check. Let's go into our course and see what the deliverables are. So let me close out all this stuff since I'm not going to be doing any more computations. Okay, so let's see here. Let me log out. Let me log back in, and let's see what our deliverables are. Now I have to post the live lesson 2 quiz questions. I'll be doing that. I will post that in the announcements section. Okay, so for Module 2, what do we have to do here? Okay, so for Module 2, you have the quiz that closes on Sunday, the live lesson quiz, which closes on Sunday, and what else? What other deliverables do we have? Okay, so for Saturday, you have Phase 2 course project, and then you have Module 2 homework. And your post replies are due at midnight tonight. So you have 3 things due today, and then you have 2 quizzes tomorrow that you have to reply to. So let's see here. Okay, so let's take a look at the Phase 2 report. Which hopefully you've had a pretty good start by now. All right, so looking at the discussion topics, okay, well, we spent a good deal of time talking about confidence intervals, what a point estimate is, and in the video I did explain what the best point estimate for a population mean is, and I did explain why we need confidence intervals. So you should be able to give a nice detailed explanations for this based on the video. Find the best point estimate of the, okay, so for using your data set, okay, using the data set, whichever choice you selected from Phase 1, find the best point estimate of the population mean, okay. All right, and then construct 2 confidence intervals for the population mean for the 95% and 99%. Assume that your data is normally distributed and the population standard deviation is unknown. Okay, so if the population standard deviation is unknown, then that means you'll probably have to use a t statistic, right? T alpha over 2. Okay. So this is an occasion where you'll need to use your equation editor to show the formulas that you're using. Okay. Then summarize your results. Say I'm 95% confident that the population standard deviation or the population mean falls within this interval, and then you compare. Yeah, so you compare your 2 intervals. So that's what I'm expecting to see. An interval estimate for the 95% confidence level and an interval estimate for the 99% confidence level. So you don't have to be too verbose. You can just write it directly. And then you have your conclusions. And then minimum of 2 pages. Okay, so I think you can do it in 2 pages. You shouldn't need more than 2 pages to do this. Okay, so get that done. All right, so that's your Phase 2 report. Then you have homework. Okay, so let's see what the homework is all about. Okay, so the homework consists of how many questions? 10 questions. Oh, it's already on my disk drive. Let me see if I can pull it up. Excellent, right? So let's see what the homework is. So for the homework, your homework submission has to be a Word document, and you will have to use the equation editor perhaps on some occasions. So question 1, it looks like we've analyzed. Question 2, 3, okay, so it looks like we've done pretty much most of these questions in the video lecture. Yeah, question 7, question 8 are chi-square distribution problems. Question 9, looks like another, what, chi-square distribution problem? Yeah, so you have all of the necessary information to process the homework. Okay, all right, so get that done. Get your phase 2 report done. Okay, then you have all the information you need for your module 2 quiz, and so what I need to do is I need to post the live lesson participation quiz question or questions. I will post that in the announcements section, so look for that in the announcements sections. Also, the link to the live lesson video, there will be 2 of them, one for an MP4 that I post on YouTube, and then one for the WebEx. Okay, all of the links will be posted in the announcements section and possibly in the what is it, the lounge, course lounge. I'll try and post them there. I noticed quite a few students were asking me where are the links to the live lesson videos, and so I don't know if I can answer too much more than that. Check the announcements. Okay, so please pay attention to that. Okay, so that is it for now. Look out for the live lesson quiz questions.